In this tutorial, we will be discussing the Chatlier's principle. A system at equilibrium can be altered by changes in its concentration, pressure or volume, and temperature, which actually affects its equilibrium constant. The outcome on the system's equilibria is governed by the Chatlier principle. If a system at equilibrium is disturbed, the system tends to shift its equilibrium position to counter the effect of the disturbance. So let's focus on concentration first. It does not change the actual value of K, which is the ratio, the equilibrium expression, that remains the same. The system will move away from the stress, only the concentrations themselves change. So let's consider this reaction. Calcium carbonate reacts to form calcium oxide and carbon dioxide. What's the effect of adding additional CO2? So we're adding stuff to the right-hand side. Because we're putting stress on the right-hand side of the equation is going to try to counteract that by shifting to the left, to shift away from that stress. What is the effect of adding additional calcium carbonate? We're adding stuff on the left-hand side now. So the equation is going to shift in a way to relieve that stress. So therefore, it's going to shift to the right. Let's do another one. Considering this equation in the bottom. What's the effect of additional bromine? Once again, bromine is on the right-hand side. Therefore, the equation is going to shift in a direction to try to relieve that stress. So since it's on the right, it's going to shift to the left. What's the effect of adding additional BrNO right here? It's on the left-hand side. It's going to shift to the right to relieve the stress. Pressure does not change the value of K. The ratio of the equilibrium expression remains the same. An increase in pressure or a decrease in volume, notice that those are one and the same, will cause the system to shift on the side with the fewest gas moles. A decrease in pressure or an increase in volume will cause the system to shift to the side with the most gas moles. So this time we're actually adding up the number of gas moles in the equation. So here's a picture. On the left-hand side, we have 1 mole of nitrogen and 3 moles of hydrogen to add up to 4 moles. On the right-hand side, we have 2 moles of ammonia. So 4 is greater than 2. So if we decrease the volume, the system's going to shift towards the side with the fewer moles of gas. So therefore, it's going to shift towards the right because 2 is smaller. Same equation, so we have 4 on the left and 2 on the right. If we increase the volume or decrease the pressure, the equation is going to shift to the side with the more moles of gas. So it's going to shift to the left. So let's take this equation. If the pressure is increased or the volume is decreased, what will happen to the system's equilibrium? So we have 1 mole of N2O4 and 2 moles of NO2. Make sure that you're only looking at the gas molecules. So we are decreasing the volume. As soon as you see volume or pressure, you want to think number of moles. So therefore, if we're decreasing the volume, once again, we're going to shift towards the side with a fewer number of moles. So since N2O4 have a fewer number, it's going to shift to the left. Alright, so let's do a few more. Let's take this equation. This is a solid, so we're not going to count that one. This one's also a solid. Oxygen is our only gas here. What is the effect of decreasing the volume of the reaction? So we're making it smaller, so we're trying to get rid of the gas molecules. So it's going to get away from the gas. So it's going to shift left. It's going to go to the side with a fewer number of gas moles. moles of gas. If we increase the volume, it's going to shift to the right. It's going to increase, it's going to go to the side with the more gas molecules. Adding an inert gas to the constant volume. That's different than what we've talked about before. Remember, these are ideal gases, and according to Dalton's partial pressures, adding more gases don't affect the overall pressure. And since it's at a constant volume, there is no change. Because there's no change in pressure nor change in volume. Okay, let's do one more set. What is the effect of decreasing the volume? So let's look at our gases. Gas here, here, and here. All three of them are gases. So we have 2 for SO2 and 1 for O2. So we have a total of 3 on the left. We only have SO3 on the right. So we only have 2 on the right. If we decrease the volume, we want to go to the side with fewer moles of gas, which would be on the right-hand side. Increasing the volume. Increasing the volume, we want to shift towards the side with the more moles of gas. So this time we're going to shift to the left. Temperature change results in a change of Kc. Consider the fizz of a soft drink. The carbon dioxide is dissolved in the solution along with heat. Once heat is added, carbon dioxide is released as a gas and left over with water. So therefore, the equilibrium constant can be looked at as the pressure of the CO2 that's given off over the concentration of the CO2 that's in the solution. An increase in temperatures puts stress on the reactant side. Therefore, it'll move away from the stress, shifting it towards the product side, shifting it to the right. The pressure of the CO2 increases and the CO2 in concentration decreases in the solution. The equilibrium ratio changes as a result, so the K value changes. A decrease in temperature would cause the system to shift to the reactant side, to the left, and the value of K would decrease. Alright, so let's look at these in practice. So we have calcium carbonate reacting to form CaO and carbon dioxide. Calcium oxide and carbon dioxide. What is the effect of increasing the temperature? This is an endothermic reaction, which you may remember means that you have to add heat to it in order for it to work. Increasing the temperature is like increasing the heat on this side. So therefore it's going to shift to get away from that. So therefore it's going to shift to the right. If we decrease the temperature, it's like we're removing this, and so therefore the reaction is going to shift to add more of that heat. So it's going to shift to the left. This is an exothermic reaction, which means heat is given off. What is the effect of increasing the temperature? So we're increasing the stuff on the right-hand side. So therefore it's going to shift away from that heat, so it's going to shift to the left. If we decrease the temperature, we're taking this heat away, and so therefore it's going to shift to the right to relieve that stress. Catalysts do not change the value of K. And they also do not have an effect on the system's equilibrium position. There's no shift. A catalyst only affects the rate of approach to the equilibrium, not the equilibrium itself. Catalysts increase the rate of both the forward and reverse reactions. So if we look here, this is what it would be without a catalyst. This is with a catalyst. The end result is still the same. So its starting point and ending point is still the same. So the equilibrium constant is the same. It's just getting there on a faster rate. So here is if it was uncatalyzed, and here is if it was having a catalyst. It just jumps to that equilibrium point faster. When one uses a catalyst, equilibrium is achieved faster, but the equilibrium composition remains unaltered. And that is the Chatlier's principle. Finally, Jesus Christ.